I welcome to all the students here in the first lecture of just 10-week classes. So in this 10 weeks, we are going to discuss everything which is required for JEST examination. We will be covering the theory in brief, um, all the formulas which are required, all the tricky points which are required, and what are all the angles in a theory which are necessary to be seen. We will be focusing more on the graphical analysis. We will be focusing more on the analytical understanding of the formulas. How do we perform integrations? How do we perform mathematical algebra? And all of these things we will be discussing. I am starting this course with the very important subject, which is thermodynamics and statistical mechanics. Why it is very important? Because in last 3-4 years, thermodynamics is coming in a huge proportion, not only in just exam but also in your gate and CSIR net and IIT jam exam as well. So today I'm going to begin with thermodynamics. After every class, you will receive both notes of the class, which are well formed. You can easily read the notes. And also you are going to get an assignment after every class, which is based on the content that we cover in a class. So sort of gives you a daily practice. In our classes, I'm going to cover all the JEST PYQs as well as 500 more problems from different exams or from the books like Singage and so on. So let's begin. You do not need any prior information or any prior knowledge to attend these classes. These classes will focus more on the problems than the theory, but enough theory will be covered so that no one lags behind. So even if you have don't know knowledge before, enough theory will be covered to bring you to the level where you can solve the problems. Okay. So let's begin with our first topic, which is thermodynamics. It is basically a class 11th topic. But many questions are coming from this simple topic. And I will also give you some BSc and MSc level ideas in today's class. So thermodynamics. In thermodynamics, the first concept we studied was work, which is basically thermodynamic work or PV work. We call it as a PV work. The formula that we know is work done is equals to integration of P dV. P is the pressure, dV is the change in volume. Because we know that work done is given by force into displacement, and force is given by pressure into area. So area into length becomes volume. That is why we know that work done is given by P dV. In thermodynamics, it is known as PV work. In thermodynamics, there are other work also possible, which are non-PV work. So that we will study in the later stage. There are some works which are non-PV work. Okay? The most common work that you understand is a PV work or thermodynamic work. So whenever gas expands or compress, it can have work. And in this, the P is basically focusing on the pressure due to the gas or by the gas, okay, or on the gas. So we focus on the pressure in which the gas is involved. Okay. Now, next point, work done can also be calculated using the PV graph. So this also you might have studied in class 11 that we have PV diagram. If you have PV diagram, the area under the PV graph gives you work done. If your graph is clockwise, then the work done is positive. And if your graph is anti-clockwise, then the work done is negative. So here I have given the two graphs. So let's calculate the work done in both the cases. This is our first graph. Now, in this first graph, you tell me, will the work done be positive or negative? Chat box, everyone in the chat box. Work done positive or negative? Yes. Negative. Okay, very good. So it is negative, it is anti-clockwise. Okay. It is a triangle and the area of the triangle is given by half into height into base. You can calculate the height of the triangle, which is P2 minus P1, and the base of the triangle is V2 minus V1. So the work done is given by half P2 minus P1 into V2 minus V1, and I have put a negative sign because I know that work done in a clockwise process is negative. Okay. On the other hand, if I have just simply this process, I am going from pressure P1 to pressure P2, like just one line. Then the area under this is all of this. This is entire area under this. Okay. Can anyone tell me what is this shape called? What is this shape called?
Trapezoid.
Trapezoid, trapezium, right? So this is a trapezium. So we need to calculate the area of trapezium. The area of trapezium is given by half of sum of parallel sides into base. Half of sum of parallel sides into base. So this is half sum of parallel sides. So sum of one parallel side is P1 and another parallel side is P2, because this length is P1, this length is P2. So sum of parallel sides is P1 plus P2. And the base is given by V2 minus V1. So V2 minus V1. So in this case, tell me, will the work done be positive or negative? Yes,
Positive.
positive. In this, you don't see anti-clockwise and clockwise. Instead, what you see is that your volume is increasing, right? Your volume is increasing. So that is why it is positive, because it's not a closed system. So you don't see anti-clockwise, clockwise. Instead, you see that your volume is increasing. Okay, perfectly fine. So this is a simple concept of about work done. At this moment, this much is enough for work done. We will include more in first law of thermodynamics. Comes internal energy. What is internal energy of the molecules? So imagine a container, and in this container you have gas molecules. So these gas molecules contains two kind of energies. One is kinetic energy and one is potential energy. Kinetic energy is because of the thermal energy, because of the temperature. Because your molecules are moving here and there, because of the temperature, that is why your molecules have some kinetic energy. Okay, or it has some thermal energy. This energy is calculated using something known as equipartition theorem. Also, in some gases, there is a interaction between the molecules. For example, two molecules attract each other or two molecules repel each other. Basically, there is a force between the molecules. Whenever there is a force between, there is also something known as potential energy. So potential energy in a gas comes when there is a force between the molecules. And this interaction can be calculated, or the potential energy can be calculated using something known as virial theorem. We will study both today. How do we tackle kinetic energy? How do we tackle potential energy? For ideal gases, there is no intermolecular interaction, because if it's an ideal gas, two molecules do not interact with each other. So the potential energy is zero. It means that for ideal gases, internal energy is equals to kinetic energy. Simply, internal energy is kinetic energy or internal energy is thermal energy. There is no potential energy in ideal gases because there is no intermolecular forces between the ideal gases. Okay, this is one of the assumptions. So let's calculate this kinetic energy part. This kinetic energy part comes from something known as equipartition theorem. Okay. Equipartition theorem. Equipartition theorem says that average kinetic energy per molecule is given by F by 2 kBT. Kb is a Boltzmann constant, universal constant. Capital T is a temperature, and F is known as a degree of freedom of the molecule or the atom or the particle, which simply means degree of freedom means that how many coordinates how many coordinates are required to describe the system, to describe the energy of the system. Let's write this. Describe the energy of the system. For example, if I am a particle and I am moving in one dimension, then I only need Vx because only need kinetic energy. So half mvx square. I only need one coordinate to find my kinetic energy. But let's say I start moving in three dimensions. So I also need Vx, Vy, Vz. Only then I will be telling my total energy, which is half Vx square, half mvy square, and half mvz square, because I have kinetic energy in all three directions. Or you can say three directions are giving me kinetic energy. Now let's say I also start rotating. Other than moving, I am also rotating. So the angular energies, angular kinetic energies will also come. Half I omega square, so on. So I will start rotating. So if I start vibrating, then some more parameters are required to describe my energy. So I can get energy in three ways. One, by translational motion. Translational motion means moving in lines either x, y, z. Through rotational motion, which basically means rotating around x-axis, y-axis, z-axis, or through vibrations, because my molecule can also vibrate. So my molecule can do three things. As a result, three kind of variables are required to describe the system. So F is known as the total degree of freedom. How many coordinates you require to describe the energy of this system? So if F is the answer, let's say F is the degree of freedom, then the average kinetic energy of my particle or for one molecule will be given by F by 2 kBT. This is equipartition theorem. Equipartition theorem word means equally partitioned, means every degree of freedom is getting the same energy, which is half kBT. Every degree of freedom is getting the same energy, same kinetic energy, half kBT, which basically means if I am translating, also my kinetic energy is half kBT. If I start rotating, because of the rotation also my kinetic energy will be half kBT. So every degree of freedom gets the equal energy, which is half kBT. That is why it is known as equipartition theorem. If you have n number of molecules, you simply multiply it with the n. It gives you F by 2 n kBT. Sometimes the number of molecules is not given. Number of moles is given. Okay, number of moles is given. So can you tell me, is this okay with everyone? Number of moles is given by number of molecules divided by Avogadro number. Is this a correct definition for number of moles? Everyone, what do you say?
Yes, sir.
आप बताइए जरा.
Yes.
I hope it is everyone is clear with this basic chemistry concept. Number of molecules divided by number of Avogadro number. So also there is one very fascinating result in thermodynamics which says gas constant is equals to Na into Kb. This is the interesting idea that gas constant is equals to Avogadro number into Kb. So what I can do is I can write my Kb as gas constant by Na. So keep this relation in mind. This is a good relation between gas constant and the Boltzmann constant. So you can put the value of Kb, which is given by R by Na. So what I have done is I put my value of Kb as R by Na. And this N remains here as such. And N by Na can be written as number of moles. So my average kinetic energy can also be written as F by 2 RT into N, where N is the number of moles. Or F by 2 kBT into capital N, where capital N is the number of molecules. Both are different. How many moles of the gas you have is a different thing. How many number of molecules you have is a different thing. So kinetic energy can also be written as F by 2 kBT into capital N or F by 2 RT into small n. That is why sometimes you see the formula F by 2 RT. Sometimes you see the formula F by 2 kBT. I hope it is clear then when to use which one and how to go from one formula to another. Is it okay? Perfectly fine. All these three things. Yes, till this point. Everyone is clear with this? Any doubt here? Yeah. So perfectly fine with all of you. Any confusion, even little bit of it? Okay. So we understood something. So first thing that we understood is how to write kinetic energy. How to write kinetic energy. Average kinetic energy is given by F by 2 kBT, where F is the degree of freedom. It is for one molecule. If it is for capital N molecules, you simply multiply by capital N. If you want to write this formula in terms of number of moles rather than number of molecules, you simply use the formula which says Kb equals to R by Na. So you can put your Kb as R by Na. This is given as number of moles. So what you have done is you have simply replaced your formula from number of molecules to number of moles. Okay? So that is a beautiful thing. So now I know how to write kinetic energy. For ideal gases, as we already discussed, that internal energy is only kinetic energy because there is no potential energy in ideal gases. In ideal gases, no interaction, no potential energy. So internal energy and kinetic energy are equal. It means all these three formulas are the internal energy of my ideal gases, because ideal gas internal energy and kinetic energy are equal. So through this I am able to find out that what is the internal energy of my molecules. Okay, in case of ideal gas, if it is one molecule then F by 2 kbt, if it is n molecule then n times F by 2 kbt, and if it is small n number of moles then F by 2 n times RT. We did the relation with each other. So the question here comes that how do we find degrees of freedom? So degrees of freedom is different for different gases. If it's a monoatomic gas, diatomic gas, triatomic gas, all of this, then for all the different gases, we have a different degrees of freedom. So if we have monoatomic gas, for example, neon, helium, argon, just one particle or just one atom. In this, you have translational or but no rotation, because a point particle can go in x-axis, y-axis, z-axis, but it cannot rotate. Point cannot rotate. There is no meaning of point rotating. So that is why a point particle can only translate. Okay? It can only translate. It can translate in x, y, z. So there can be three translational degrees of freedom, because it can go in x, y, and z. So there are three degrees of freedom which are possible. We come diatomic. So right now we are only focusing on translational and rotational. We are not focusing on vibrational. So there are three kind of motion which are possible: translation, rotation, and vibration. We are focusing first on these two, and then I will tell you what to do for vibration. So the monatomic molecule can only translate, no rotation, no vibration, because it is just one particle. How can it rotate? Then comes diatomic. Diatomic molecules are like hydrogen gas, oxygen gas, nitrogen gas. It looks something like this. This is H and H. Now, this molecule can go in X direction, it can go in Y direction, it can go in Z direction. This molecule can go in any of these three directions. It means it has three translational degrees of freedom. And it also has two rotational degrees of freedom. It does not have three rotational degrees of freedom, it has two rotational degrees of freedom. Why? Because it can rotate around Y axis, it can rotate around Z axis, but it cannot rotate around X axis. This is a very tricky concept. Now you tell me, you tell me, if you are on a merry-go-round, so you are a mass, okay? You are a mass. Let's say you are rotating on a merry-go-round. If you come and sit on the axis, stand on the axis. So this is your merry-go-round, and this is the axis around which it is rotating. If you are standing here, then definitely you are rotating. But if you come and stand on the axis, will you still be rotating? Will you still be rotating? Yes. Everyone,
No.
if you come and stand on the X perfectly on the axis. No. So is it okay to say that if mass is on axis, it does not rotate? It does not rotate, right? And do you all agree that both the masses are on x-axis? Yes. Kya ye baat everyone agrees this, that both the masses are on x-axis? Yes, everyone agrees with. So now you tell me, can your molecule rotate around x-axis? No, because your molecule is standing on the x-axis. So your molecule cannot rotate around x-axis, because when we stand on the axis, we cannot rotate. So that is why this molecule can rotate around y-axis and this molecule can rotate around z-axis, but not along y-axis. Oh, sorry, x-axis. That is why there are only two rotational degrees of freedom, not three. Perfectly fine, everyone. Do you got the concept? Why two, not three? Yes, to all of you. Any confusion here? Yeah. Gee, chat box of everyone. It will be good to know that if you have understood, right? Perfectly fine. Sure, very nice. Now let's talk about triatomic linear molecule. For triatomic linear molecule, again, this is your triatomic linear molecule. One of the example is CO2. This is your CO2 example. You know this is CO2. I think there are two bonds only. Yeah. Now CO2 molecule has again three translation because it can go in X, can go in Y, can go in Z, and also again two rotational. Why? Because again the same logic. You can rotate around Z, you can rotate around Y, but not along X because molecule is on the X. All three particles are sitting on the X axis. That is why you cannot rotate around X axis. And then triatomic non-linear. For example, SO2 or H2O. Examples like this. They again have three translation because molecule can go in any direction, and it has three rotation also because you can rotate around X, you can rotate around Y, and you can rotate around Z. Okay, so you can rotate around all three, but so that is why you have three possible rotational degrees of freedom. I hope it is clear that how to find degrees of freedom for all four categories. G. Can we now include vibration? If you are all ready, I will include vibrations now. Very good concept. Yes. G, can we move on? Yeah. So let's move on. Let's start with the vibration concept. Now, when the temperatures are very high, if I make the temperatures very large, what happens is the atoms inside the molecule start vibrating. For example, let's say diatomic molecule. This is hydrogen, this is hydrogen. If the temperatures are low, it is translating, it is rotating. But if you make the temperatures very high, what will happen is that these hydrogen atoms will start vibrating. Start vibrating. Okay? So if they start vibrating, so the bond length does not remain constant. Obviously, you understand this idea that if you are oscillating or if you are vibrating, the bond length between them will also start to change. So because of the vibration, the new motion is coming. Vibration motion is a new motion. And this motion is activated only at the higher temperature because you need high amount of energy to make something vibrate. Something does not vibrate by itself. You need some higher amount of energy to activate the vibrations. Right? You activate the vibrations, then only it will vibrate. So additional degrees of freedom comes because of the vibration. Some more degrees of freedom comes because of the vibration. How do we calculate those degrees of freedom? So first of all, we calculate the number of modes. How many modes of vibration are active? There are two different things in vibration. One is known as modes and one is known as degrees of freedom. Till now, we have studied degrees of freedom. Now I am introducing something known as modes. How many modes are possible in your vibration? How many possible modes are there? Okay. So if I say there is one mode, then every mode gives you 2 degrees of freedom. Every mode, each mode gives you 2 degrees of freedom. Let me, I will explain this even more, but at this moment, just trust me. At this moment, just trust me that one mode of vibration gives me 2 degrees of freedom. Why it happens, I will teach you why. At this moment, you all trust me that if in a question it is said that one mode of vibration is active, then it means there are 2 degrees of freedom which will be there. So, how many number of modes are activated will be mentioned in the question. But let's say it is not mentioned. It will be mentioned, but let's say it is not mentioned. Then how do you calculate? Then the number of modes is calculated using the formula known as 3n minus 5 if it is a linear molecule and 3n minus 6 if it is a non-linear molecule. So let's take an example of diatomic molecule. So for diatomic molecule, can you tell me number of modes? N is the number of atoms. So can you use the correct formula and tell me number of modes? Vibrational modes. Yes. Yes. Three people give the answer. Yes.
One.
One. Because it's a linear molecule, so I use this formula. And number of atoms are 2. So 3 into 2, 6 minus 5 is 1. Now, how many vibrational degrees of freedom will be there? Modes are 1. So how many degrees of freedoms will be there?
2.
2. Okay. Okay, let's calculate this. How many number of degrees of freedom of vibration will be here? Maximum. In this linear triatomic.
4.
Yes.
4.
I asked vibration degrees of freedom.
8, sir.
8, right? I asked degrees of freedom, so it will be 8. So modes are 4. Freedom degrees of freedom can be 8. So if it is mentioned in the question that how many modes are activated, then you use those number of modes. But if it is not given, and then they say, okay, all the modes are activated, everything is activated, then how can you calculate that how many modes can be activated using this formula? So I gave you the SWOD or the technology for both of them. Okay? How do we know that one mode is equals to 2 degrees of freedom? So one vibrational mode is 2 degrees of freedom. One rotational mode is 1 degree of freedom. One translational mode is 1 degree of freedom. But one vibrational mode is 2 degrees of freedom. Why? Let's see this. Degrees of freedom is also known as number of square terms in energy. How many of you have heard this line before? Degrees of freedom is equals to number of square terms. Have you heard this?
Yes.
In energy, degrees of freedom is equals to number of square terms. If you have not heard it, hear it for the first time. So degree of freedom is also written as how many square terms are there in the energy. Okay. If it is translation, so you can clearly see energy can be written as half mvx square, half mvy square, half mvz square. So basically you can see there are three square terms, so there can be three translational degrees of freedom. If you are rotating, then you must know that in rotation the kinetic energy is written like this. Let me tell you, this is my linear motion, this is my rotation motion. In linear motion, if you have mass, then in rotation motion, who do the work of mass? Who is same as mass in rotation? In rotation,
Moment of inertia.
movement of inertia. Yes. If you have displacement, can I say in rotation you have theta? If you have linear speed, can I say in rotation you have angular speed? So in linear motion, if the kinetic energy is given by half mv square, so can I say in rotation motion it will be half I omega square? Yes. Everyone clear with this? Rotational kinetic energy can be written as half I omega square. G, any doubt in this relation? Hmm? Perfectly fine. So if you are rotating, the kinetic energy is given by half I omega square. So if you are rotating around x-axis, then omega x square, omega y, then along y-axis, and then along z-axis. So you can see you can have three rotational degrees of freedom. But what about vibration? Vibration is like a simple harmonic motion. So this is your vibration. Let's say this is your vibration. Vibration is like a simple harmonic motion. And if I write the energy of vibration, so can I say it is given by half kx square plus p square by 2m? Are you familiar with the energy of vibration given by half kx square plus p square by 2m? This is kinetic, this is potential. G. Am I right? If you are oscillating, so you have potential energy also and you have kinetic energy also. Your pendulum has both. Vibration means oscillation. In oscillation, you have both the energies. One is this, and one because of potential and one because of kinetic. So how many square terms are there in this? One or two? Two square terms. Two square terms. So if you activate one vibration, this is just one vibration because this is only happening along x-axis, just one vibration along x-axis. One vibration gives you two square terms. That is why one vibrational mode gives you 2 degrees of freedom. Okay, so I hope this all till this point everything is clear. Gee, any doubt till this point?
But p square by term is another form of kinetic energy, then how it is potential?
हाँ तो ये पोटेंशियल है, ये kinetic है.
Oh.
Right? Half kx square is potential. Because when you are vibrating, for example, pendulum, when the pendulum is moving, pendulum has kinetic as well as potential, right? जी जी any doubt everyone? हो गया, clear हो गया. So one time, yes.
Sir, for CO2 molecule, the vibrational modes will be 2 and the degree of freedom will be 4. That's right.
CO2 molecule is a linear, right?
Yes.
So CO2 molecule is a linear. So you put it here. So modes will be 4. N is 3 and 4. But if you are studying particular CO2, then you will find, okay, I don't want to introduce in a simple class. If you will actually go and do the experiment, you will not find all 4 because 2 of them are non-degenerate. Okay? That is a separate molecular issue. Okay?
Yes.
As per the general theory, it should be 4, but what happens is 2 of them are degenerate. That is why in an experiment you only see 2, but actually theory-wise there should be 4. So at this moment we are studying theory. Sometimes what happens is 2 degrees of freedom gives you the same energy. In that case, you cannot able to detect it in the experiment. Okay. So I hope it is clear till this point. Agar, if you say yes, I will go to the next very important concept of heat capacities. I will clearly describe the difference between the 3 kind of heat capacities. All the confusions. जी करें शुरू करें heat capacity start. Yes. Yes. Okay. So heat capacity is what? Heat capacity describes how much heat is required to raise the temperature by 1 degree. So let's say you have some body and I ask you that what is the heat capacity of this body. So heat capacity of this body is that how much heat I should give so that its temperature increase by 1 degree, just by 1 degree. So 3 kind of heat capacities we describe. One is known as simple heat capacity, which is C. It is given by dq by dt. Heat given by change in temperature. And you can clearly see that C will be equals to dq if dt is 1. So which basically says that how much heat is required to raise the temperature by 1 is equals to specific heat. Now the problem with this definition is that this definition depend on both the material as well as the amount of substance. For example, if you have 1 liter of water and 100 liter of water, will both have same heat capacity or different heat capacity? Different or same? Heat capacity.
Yes, sir.
Different. Because why different? Because in order to raise the temperature of 1 liter water, you need less heat. In order to raise the temperature of 100 liter of water, you need more heat. So heat capacity is different for both. So the units of this is given by joules per Kelvin. This is fine. Then we define something known as molar heat capacity or specific heat capacity. So molar heat capacity is amount of heat required to raise the temperature by 1 degree per unit moles divided by total number of moles. So all I have done is I have divided by total number of moles. So when I divide by total number of moles, amount of substance becomes insignificant because now I am not talking about the total substance. I am just talking about 1 mole of substance. So now you tell me 1 mole water and 100 moles of water, will they both have the same molar specific heat or different molar specific heat?
Same.
Same, right? Why? Because now I have divided by the number of moles, so it makes the balance. That is why molar specific heat is a property of material. It is not the property of substance. How much substance you are taking, it does not matter. It depends on what is the material. If you are taking water, either 1 mole or 100 mole, molar specific heat remains same. So the units of this thing is given by joules per Kelvin per mole. Then we define something known as specific heat capacity. Specific heat capacity is, this time we are not dividing by number of moles, we are dividing by total mass. Because sometimes we study mass, sometimes we study mole. So this time we are dividing by mass. Again, it will not depend upon the amount of substance because you are dividing by the total mass. That is why specific heat also depends only on the material. What material you are taking, water, aluminium, gold, right, gas, what you are taking, it only depends upon that. It does not depend upon how much you are taking. So the specific heat is given by joules per Kelvin per gram. So three heat capacities I defined. One is normal heat capacity, one is molar heat capacity, and one is specific heat capacity. Specific heat capacity means dividing by mass. Molar heat capacity means dividing by number of moles. Heat capacity means simply dq by dt. ठीक है जी. Now, two specific heats are very famous. Two Cp and Cv. Two heat capacities are very famous. One is Cp and one is Cv. So we have to understand what is Cp and what is Cv. Now, Cp means constant pressure. Cv means constant volume. Now you can define anything, any Cp. You can define molar molar heat capacity at constant pressure. You can even define specific heat capacity at constant pressure, or you can even simply define heat capacity at constant pressure. So this thing can also be defined at constant pressure, this thing can also be defined at constant pressure, and this thing can also be defined at constant pressure. Okay? So if you are defining molar specific heat at constant pressure, so is this thing correct? Sorry, molar specific heat at constant pressure. So is this thing correct?
Yes.
Yes. Everyone? Yes. And what is this then? Is this specific heat capacity at constant pressure? Because in this you are dividing by mass. So this is specific heat capacity at constant pressure. So you can define any. So you can define even specific heat capacity at constant pressure, and you can even define molar specific heat at constant pressure. Same thing you can do for volume also. Same thing you can do for volume. So I'm defining specific heat capacity at constant volume. 1 by m dq by dt at constant volume. Now, first law of thermodynamics, I'm not explaining first law, just I'm using on the side notice. First law of thermodynamics is given by dq, heat equals to change in internal energy plus work done. If the volume is constant, then work done is zero. Because work done is given by PdV. If the volume is not changing, work done is zero. In that case, dq becomes du. So is this formula correct? Can I replace my dq with du if the volume is constant? Yes. G. Till this point, clear? Yes. So we are not exclusively using first law, just a side note. Yes. So Cv is given by 1 by m du by dt. Everyone, G. And no doubt till this point, right? Okay. Similarly, we can also define molar specific heat at constant volume. Whatever, you can define all of them. Okay. Now comes a very interesting question. Which formula is correct? C is given by F by 2 K, or C is given by R by 2K. So should I be writing my formula in terms of Boltzmann constant, or should I be writing my formula in terms of uh, gas constant, R? Should I be writing my formula in terms of R, or should I be writing my formulas in terms of Kb? So it all depends upon, yeah, it's actually both are right. So it actually depends upon which specific heat you are dealing with. Okay. So far, I have seen two formulas for internal energy. One formula for internal energy is F by 2 kBT. This is for one molecule. Another formula that I study is F by 2 N times KBT. This is for N molecules. And one formula that I see is F by 2 small m into nRT. This is for N number of molecules, moles, N number of moles. Okay. So in this case, I'm going to define the formula which is for moles. And the specific heats that I'm going, or the heat capacities that I'm going to define are also the molar heat capacities. So the more common in thermodynamics, out of these three, whenever you are writing CP, whenever you are writing CV, you can write all three. But more commonly, you will see that you are writing this one, molar heat capacity. More commonly, it is not like you cannot use other two. But molar heat capacities, you will find out in most of the questions they are using molar heat capacity. For example, have you heard this formula? Cp minus Cv equals to R.
Mayer's relation.
Yes, everyone. What is the name of this guy? Cp minus Cv equals to R.
Mayer.
Mayor. Yes. So in this, what is CpCv? Which heat capacity is it? Heat capacity, molar heat capacity, or specific heat capacity? Yes, molar heat capacity. Let's say I give you this relation. When you tell me what is most likely, is it molar or specific?
Specific.
Specific. You understand, right? You got an idea that whenever you are writing the relations in terms of R, it means most probably you are defining molar specific heat. Okay? So I am trying to define molar specific heat, and U is given to you as F by 2 nRT. This we already discussed. And this is my relation. This is my CV. My CV is given by 1 by number of moles into du by dt. So du by dt you can do. If you do the differentiation of this with temperature, do you all agree that you will get F by 2 nR, because differentiation of T will be 1. So you will get F by 2 nR, and n cancels. So you get F by 2 R. So it means CV equals to F by 2 R. So which heat capacity is this? This is molar specific heat. F by 2 R is known as molar specific heat. But let's say if I say this, CV, if I simply do the differentiation of this, then this will not be a molar specific heat. Okay? Because I use the formula 1 by n. I use the formula 1 by n. That is why the heat capacity that I'm defining is actually molar specific heat. So a simple idea that I got is that my CV is given by F by 2 R. G. Any doubt? Hanji. This confusion remains. That is why I made this clear that there are three heat capacities, and what we are calculating is actually molar specific heat. किसी को 1% भी doubt है तो you can ask. Yes, tell me. Everyone, if you are all agree, I will move on to the next point. चलें आगे. Someone who is doing it for first time, especially. Yes. Good. चलो next करते हैं. Then I have found CV. What about CP? For CP, I will use a relation which is known as Mayer's relation. Mayer's relation says CP minus CV equals to R. CP minus CV equals to R. So I can easily find CP. CP is given by CV plus R. So if I add R in this, I will get CP. So CP is given by F by 2 plus 1 into R. So this is my CP. And sometimes we also define adiabatic constant. What is adiabatic constant? Adiabatic constant is a ratio of Cp and Cv. So if I take the ratio of Cp and Cv, I will get F by 2 plus 1 divided by F by 2, which is 2 by F plus 1. Because this and this cancels, and this becomes is equals to 2 by F plus 1. So I hope everything is clear. Yes. समझ गए मेरी बात? Okay, let's find for different cases. So first, for monatomic gas, we just studied that there are three translation, no rotation. So what is CV? CV is given by F by 2 R. How many degrees of freedom are there? 3. So it will be 3 by 2r. What will be Cp? Cp you know is given by F by 2 r plus 1. So it will give you 5 by 2 r. And then gamma. Gamma is given by Cp by Cv. So it will give you 5 by 3. So now you tell me what will be the gamma for triatomic non-linear. Only consider rotational and translation. No vibration. So triatomic non-linear. Tell me the value of gamma.
4 by 3.
Yes, everyone in the chat box, tell me your answer.
Four by three.
Everyone. Yeah, more and more answers. There are 70 plus people in the class. Yes. Four by three. Everyone is getting 4 by 3. Yes. Because you know, for diatomic, there are 3. For rotational 2. So for diatomic, you can easily find. Then we will need to find for triatomic non-linear. So for triatomic non-linear, there are 3 translational, 3 rotational. So total are 6. So CV is 6 by 2, 3R. And CP will be 4R. And gamma will be 4 by 3. Done. Sure. Let's do some of the PYQs. So for which of the gas Cp by Cv is largest? Monatomic, diatomic, triatomic, hexaatomic? Yes.
Monatomic.
Monatomic.
Yes, everyone. You can check this. Who is larger out of 4?
Mon-
Mono. Can you check, everyone? So, and also you can see gamma is given by 2 by F plus 1. So more the degrees of freedom, less is the gamma. Less is the degrees of freedom, more is gamma. The minimum number of degrees of freedom are in mono. So the maximum gamma will also be in mono. So that is why the maximum gamma is in mono. Next, this is your JEST PYQ. Next, this is your CSI net PYQ. Consider the 1 mole. You see, mole. It means which specific heat should we define? Molar specific heat. Ideal diatomic gas. Diatomic gas is given to me. So in diatomic gas, translational degrees of freedom are 3. Rotational degrees of freedom are 2. They are at a temperature such that kBT is much greater than h nu. So is it a high temperature or a low temperature?
High temperature.
Higher temperature.
Everyone. High. So how many vibrational modes will be there? We already discussed for diatomic 1. So how many vibrational degrees of freedom will be there? 2. We talked about the diatomic case 3 and minus 5. And if n is 2, you get 6 minus 5, which is 1. So one mode is there. So 2 vibrational degrees of freedom are there. So what is the total degrees of freedom? 3 plus 2 plus 2, 7. And what is the value of gamma?
9 by 7.
So did everyone got 9 by 7? G. So this is a very latest question from CSI. So I hope it is clear. You are getting the idea now. ठीक है जी? Sure. Yes. If all of you are okay till here, then we go to something known as virial theorem. Yes. जी. करें भी आगे बात? So let's talk more. Now we come to something known as virial theorem. Why do we need virial theorem? First of all, that is very important because once we know why do we need, only then in the question we will be able to use. देखिए virial theorem का what is happens with virial theorem. See, your total internal energy is given by kinetic energy plus potential energy. Then I said kinetic energy you can calculate using equipartition theorem. And I said potential energy is 0 if you are in an ideal gas. But what if I am not an ideal gas? What if I am a normal particle? In that case, my potential energy will not be 0. So I also need to calculate potential energy. I have already calculated kinetic energy. Okay, kinetic energy. And now we also need to calculate potential energy. And potential energy can be calculated using known as virial theorem. Because virial theorem gives you the relation between average potential energy and average kinetic energy. Because you already know kinetic energy, and if someone gives me the relation between kinetic and potential, then I can also find potential energy. So virial theorem gives me that relation. So what does virial theorem says? Virial theorem says if your potential is dependent upon r to power alpha. For example, if potential is given by 2r3, then alpha is 3. It means my potential is dependent upon r cube, r to power alpha. So if my potential is dependent upon r to power alpha, then average kinetic energy is given as alpha by 2 times average potential energy. So in this example, my average kinetic energy will be equals to alpha by 2 times average potential energy. I already know average kinetic energy using equipartition theorem, so I can easily find average potential energy. So this is my virial theorem. Virial theorem says if V is proportional to R to power alpha, then kinetic energy is proportional to alpha by 2 times average potential energy. What if I don't tell you how does your potential depends? Instead, I tell you how does your force depends. For example, if I say force depends upon, or force is equals to 2 times R5. So if force depends upon R to power 5, then how does potential depends upon R? So is it okay to say force is equals to minus curly V by curly R? Is it okay to say that force is potential is equals to integration of force? So if force is dependent upon R to power alpha, so can I say potential will be dependent upon R to power alpha plus 1? Is this bracket okay to all of you? Have you heard about this relation somewhere in BSc or MSc? Yes. Any doubt in this one? If I say force is dependent upon R to power alpha, is it okay to say that potential is dependent upon R to power alpha plus 1? G.
Yes, sir.
Yes. So then my relation will become average kinetic energy equals to alpha plus 1 by 2 times average potential energy. For example, in this case, my average kinetic energy will be alpha plus 1, which is 6 by 2 average potential energy. So I hope it is clear that if force relation is given, how you can find the relation between them, and if the potential relation is given, how you can find the relation between them. Okay. How can I find average kinetic energy? Average kinetic energy you already know from equipartition theorem, F by 2 times kBT. And now you can easily find the relation between them. So the total energy will be equals to kinetic energy plus potential energy. This comes from equipartition theorem and this comes from virial theorem. करें भी questions करें? Can we go to the questions? Yes. Everyone have this noted down in their notebook. Can we do the questions? Yes.
Yes, sir.
What do you say? Sure. Let's start with the JEST PYQ. For a classical system of non-interacting particles, simple particle, in the presence of spherically symmetric potential, you see, so gamma r cube, what is the mean energy per particle? So let's first find kinetic energy. Okay, by looking at r, can you say it is 3D? If it is not given, you always take it as 3 dimensions. G. R is radius, means you can easily take it in 3 dimensions, right? So I can assume that I am in 3 dimension. No word in this question stops me from that. So I am taking 3 dimension. My motion is in 3 dimension. If it is not mentioned, always take 3 dimension. If it is mentioned 1D, 2D, only then take 1D or 2D. If it is not mentioned, it is by default 3 dimension. If it is a point particle, it will only have translational degrees of freedom. No rotational, no vibration, because it is just point particle. So translation, it can move in x, y, z. So how many degrees of freedom does this point particle has? 3. So what will be its average kinetic energy? 3 by 2 kBt. Okay. In order to find average potential energy, I need to use virial theorem. Virial theorem says if my potential is r cube, it means my alpha is 3. Then my average kinetic energy is equals to alpha by 2, which is 3 by 2 times average potential energy. So I put my value of average kinetic energy as 3 by 2 kBt. I also have 3 by 2 here, so that cancels. It means my potential energy comes out to be kBt. So this was my kinetic energy and this is my potential energy. And then my total energy will become 3 by 2 plus 1, which will be 5 by 2 kBt. So this gives me option number B. Is this difficult just question clear to all? Yes. Have you understood how to modify equipartition in this case? Why I modified? Because potential was there. So in order to additionally add potential, I need virial theorem. Everyone, now this was a difficult question, so I need everyone's approval. Are you clear with this question? Ji, in the chat box. Yes, Preetham, I can definitely repeat. You see, it is 3 dimensions, so the average kinetic energy is 3 by 2 kBt. Okay. Then I need to find average potential energy, which is using virial theorem. So I know the relation between kinetic and potential. Kinetic is given by alpha by 2 times potential. I put the value of kinetic here. So I also get potential. I also get potential energy. I have kinetic, I have potential. I simply add them to get the total mean energy, which is 5 by 2 kBt. Chalo, if you are so clear, tell me the answer to this question. This is
Sir?
net PYQ. Yes.
Sir, this relation comes from where?
Virial theorem from classical mechanics by using the Lagrangian mechanics. Virial theorem is a theorem in classical mechanics. Like equipartition theorem is a theorem. Okay. Yeah. If you are asking for the proof of this,
Yes, sir. How can we prove it?
I will share the video in the group. Okay.
Okay.
How you can visualize it or how you can prove it.
Okay.
Okay. Okay, everyone. Now tell me the answer to this question. It has both kinetic energy as well as potential energy. And it is one dimensional. So first of all, if it is one dimension, tell me average kinetic energy. Yes.
3 by 2 kb.
3 by 2 in one dimension.
1 by 2 kb.
Okay.
In one dimension,
is 1 by
in one dimension, 1 by 2 kBt. If it is one dimension, only 1 degree of freedom you have. Everyone clear with the average kinetic energy? Now for potential energy, what is the value of alpha?
4.
4. So can I say average kinetic equals to 4 by 2 times average potential? So average kinetic is given by what? Average kinetic is half kBt equals to 2 times potential energy. So potential energy becomes 1 by 4 kBt. So this is your potential, this is your kinetic. If you add them, what is an answer that you get?
B.
Yes.
3 by 4 kb.
Yes. Do you get B, everyone? एक बार भाई जल्दी से जकारा शेरा वाली का B आ रहा है भाई सबका? चलो, very good. I hope it is clear. Done. ठीक है जी. Good. Now comes a question which is mind blowing. मतलब in this you cannot directly use virial, directly cannot use equipartition. So now hold your belt tight. This is the last question for today, and listen to this question very carefully. Consider a system of classical non-interacting particles moving in xy plane. So you are moving in 2 dimensions. And the potential is given. It means you are moving in 2 dimensions, so you have kinetic energy. But also you have some potential energy. So what is the average energy? Now, many people will say it is a very simple question. How it is a simple question? You will say it is 2 dimension, right? So average kinetic energy is given by 2 by 2 kBt, F by 2 kBt, F is given by 2. So average kinetic energy is kBt. And then you can say, okay, potential is directly proportional to square. So alpha is 2. So average kinetic energy is given by 2 by 2 times average potential energy. So it is kinetic and potential becomes equal. Okay. So average potential energy is also kBT. So the average is 2 kBT. And if you see the option, it is also there in an answer. So C is correct. It is actually wrong. It is actually wrong. Why it is wrong? Because it is not simply x ka square or simply y ka square. It is x minus y square. Okay? So directly using and jumping and using the virial theorem will be wrong. So we have to be very careful in this respect. Virial theorem is not wrong. I will tell you why virial theorem is okay. But listen to this question very, very carefully. सुनो जरा इस क्वेश्चन को जरा listen to this very nicely. Can I say x minus y and x plus y will be the two independent variables? This is first idea. How do you decouple the equations? How do you decouple the equations? If you have decoupling of the equations, how do you decouple it? X minus y and x plus y, usually what we say is we define new parameters. Because the problem here, what is potential? The problem is I neither have x square, I neither have y square. What I have is x minus y square. So I need to decouple them. Decouple them means looking at it at x separately, looking at y separately. So usually when we need to decouple, we define two independent variables. One is x. So let's say x minus y is one variable u and x plus y is another variable v. These are the two new variables in your equation. Two independent variables. U is independent and v is independent. Two different independent solutions. So I define, so what I'm trying to do is I'm trying to write my potentials in terms of u and v, new parameters, some new parameters. So one parameter is u x minus v and v x plus y. So u is x minus y and v is x plus y. So what will be differentiation of u? Differentiation of u will be differentiation of x minus differentiation of y. So u dot will be x dot minus y dot. Similarly, v dot will be equals to x dot plus y dot. So from these two, are these two correct? Yes. From these two, are these two correct? Yes. जी, everyone, can you see
Yes.
this? Yeah. In the end, I will also prove you that why this u and v are independent. I will also show you that why u and v are independent. This is very important. Okay, chalo. Can I write my total energy as half m x naught ka square plus half m y naught ka square, and this is my potential. This is my potential. Because kinetic energy plus potential energy. Kinetic energy is given by half m vx square. Vx is what? Dx by dt. Dx by dt can be written in simple words like x dot. So half m x naught square, half m y naught square, and half f alpha x minus y ka square. Because this is given. I'm not doing anything. This is simply given to me. Now I replace x and y in terms of u and v. If I do that, can I put my x naught as this? And can I put my y naught as this? And x minus y ko I can write u, because x minus y is simply u. How many of you agree that these two will give me this? Try to see this maths. Yes. Yes. How many of you agree this? Agree? Everyone?
Yes, sir.
Everyone agrees, right? Denominator is not 4, because if you square, you get, yes, 4. 4. Because you are squaring, so 2 will add and it will get 4. Okay, thank you. 4. Although that does not matter. That does not matter, but 4. So this is what we have. So it is 1 by 4 m u naught square, 1 by 4 m v naught square, and now you only have u. So by looking at this equation, can you say this u and v are independent variables? They are not coupling each other. U and v are now independent variables. By looking at this equation, is this much easier to handle? Yes. Yes. What do you think? So now can you see u and v being independent variables of each other? जी क्या बोलते हो मेरे भाई? Yeah. Yes. Tell me. नहीं clear हुआ ये?
Yes.
This equation is correct, right? So all I have done is written my equation from xy to uv, nothing else. By doing so, what problem I have solved? The problem that I have solved is that when I was writing my equation in xy, they were coming together. But when I'm writing my equation in uv, are u and v coming together or separately in every term? Separate or combined?
Separate.
Separate. So yes, we are changing the basis. Yes, separate. Decoupling. How many square terms are here? How many square terms are here?
3.
3. So can I directly say my energy is 3 by 2 kBT? So that is one way of doing it. Now try to apply virial theorem. Now apply virial theorem. So one term is giving you kinetic energy because of U. One term is giving kinetic energy because of V. So the average kinetic energy because of U is 1 by 2 kBT. Average kinetic energy because of V is also 1 by 2 kBT. Now let's try to understand the virial theorem. Virial theorem says that if your potential energy is directly proportional to U square, this is your potential energy, and this is directly proportional to U square, then your average kinetic energy is, this is your alpha, so 2 by 2 times average potential energy. So average kinetic energy is equals to average potential energy. So now I ask you the question, should I use total kinetic energy here or only the kinetic energy because of U? Yes. Because potential energy is only because of which?
U.
Potential energy is only because of U or both? Potential energy is only because of U or both? Yes.
Only because of you.
U. So I should only be using kinetic energy because of U, which is given by half kBT. It means average potential energy is also equals to half kBT. ठीक है? Half kBT. ठीक है जी? Simple idea. So that is my understanding. So average potential energy also comes out to be half kBT. And these are, so basically average kinetic energy because of U half kBT, average potential kinetic energy because of V half kBT, and average potential energy also half kBT. So that total energy is 3 by 2 kBT. This is much easier to see that there are 3 square terms. So 1 by 2 kBT because of this, 1 by 2 kBT because of this, and 1 by 2 kBT because of this. Two of them are kinetic energies, one of them is potential energy. So the answer to this question is 3 by 2 kBT. Yes. Am I able to satisfy your brain for this question? Yes.
Sir, what if u की power 1? Then we get 2 square terms only. Then degree of freedom is 2. But if we solve by using virial theorem, then it comes 1 kBT from the kinetic energy and only half kBT from the potential energy terms, the virial theorem. Then it is 3 by 2 kBT. But it is
तो अगर 1 होता तो मैं वो करता
all
था.
type.
अगर 1 होता, देखो, पहली बात, when there is a 1, you don't use virial theorem in every situation. ठीक है? Okay. Understand. If your potential is directly proportional to 1, ठीक है? Is equals to 1. It means your force is not even depending upon the position. It's a constant force. ठीक है? Because F is equals to curly U by curly X. And it is depending on x to the power 1. So your force is constant force. So constant force. So for constant forces, averages are 0. Or you can understand like this. If your U is x to the power 1 and if you're trying to find the average, then half of it is a negative, half of it is a positive. ठीक है? तो
Yes.
हर जगह पे we cannot use virial theorem, because then wherever you see contradiction, for example, you have found the contradiction that if u is 1, then see, if it is not a square term, if it is not a square term, then we use virial theorem. For example, in the previous question, was this the square term? In my Hamiltonian, was this the square term? No, right? This is not a square term, right?
Yes.
You can clearly see. है ना? So how did I find the contribution because of this? Using virial theorem. But in this, I don't have to dedicatedly apply virial theorem because it is already a square term. I know that degree of freedom is directly equals to square term, but I can even use virial theorem. For example, I have showed you how to use virial theorem. That also I have showed you. Okay, so that is the idea. Yes.
So
Hmm?
if u is 1, then we take only this.
I cannot make this statement. U is 1 and it is coming because of which contribution. When looking at the entire question only, we decide. Okay.
Okay.
Yeah. So in this question, what I started with this, in this question I started that, oh, there is x and y coming together, so they are coupled. So I define two new variables. One is u x minus y and one is v x plus y. So my this equation becomes this equation by replacing my variables this equation. Now in this equation is very simple to deal with because there is one square term, so this gives me half kbt. Another square term, so this also gives me half kbt, and another square term which is also giving me half kbt. So the energy, total energy of this is 3 by 2 kbt. Yes, clear, clear. छोटा सा एक लास्ट और करें. हाँ जी.
Sir, if one term we will get in which both u and v are present, for example, half uv, then for that,
हाँ,
what will be kinetic energy?
no, if you are getting, for example, in this I was getting such situation, right? X square y square minus 2xy, right? I was
Yes.
getting xy, right? So did I directly started using virial theorem, or first I try to decouple them, right?
Yes.
So first, whenever you see multiplications, rather than using the theorems, you first decouple them. Because if you decouple, only then you can easily apply your virial theorem and equipartition theorem. If you will apply them to any situation, for example, in previous cases, there was no decoupling. You see only x4. So I can easily use it. In this, you can directly see only r cube. So I can easily use this. So I can easily use virial theorem in these two questions because there was no coupling. But in this, you see x and y variables was coupled together. They were in one equation. So
Yes.
I had to decouple using the smart trick in which I said, let's say x minus y is one variable and x plus y another
Sir,
variable.
and we cannot do like this, u is equal to x minus y, and v also is equal to x minus y, as it is x minus y whole square.
नहीं, अगर आप u is also x minus y, v is also x minus y, then u and v are equal.
Yeah.
So obvious, that is obviously one. Because not only we have to replace this, but we also have to make sure that x naught and y naught are also replaced, right? Because you see, why this trick helped? Because in x naught ka square, you see, you came out to be 2 u naught v naught, right? And from y naught ka square, you got minus 2 u naught v naught. You see, so the couple term got cancelled out, right?
Yes.
Why this trick was so, you can say, filthy technique, yeah? So yes. Okay. So can I just take 5 more minutes, everyone? Just few formula, 2, 3 formulas which
Sir,
I will give you. We will, yeah. Tell me.
sir, everything is clear, but can you repeat that why we cannot apply virial theorem when
We can.
our potential is मतलब कि basically it has power in squares and मतलब कि why we cannot apply?
No, we can. We are applying here. If you apply virial theorem to this, you still get the same answer.
सर वो आप उसको कुछ बता रहे थे ना उसके बारे में कि अगर
नहीं
ये
वो कह रहे थे कि if in this we simply have half alpha u like this. Hmm? So should we apply directly virial theorem? I said we can, but before applying, we always make sure that what is our question. है ना. What is been asked, what is U, what is average, समझ रहे हैं. So that is an idea. So I said before we apply virial theorem, always we understand the question first. ठीक है, तो ये मैं उसको बस बोल रहा था. I'm not saying we
तो
cannot.
बेसिकली पोटेंशियल जो है वो हमेशा मतलब कि ये मिनिमम ये 2 का पावर उसका होगा, ये आप कह रहे हैं या क्या?
No, no, मैं ये भी नहीं बोल रहा हूँ. मैं again I'm saying that अगर क्यूब हो, यूजुअली आप देखेंगे कि either it will be u square or u4 or u6, because in the cases of u cube, u5, there are some more techniques, है ना. अगर ऐसा कोई क्वेश्चन है, फॉर एग्जांपल आप देख भी सकते हैं. You see, in this question it was x4, right? In this question it was r cube. So in this we were able to apply because it was r cube, so no problem. But अगर r आ जाता है, so if I, अगर आप ध्यान से देखेंगे, if my potential is just simply proportional to x, then my force is not proportional to x. ठीक है, so इसको बोलते हैं कांस्टेंट फोर्स. उस केस में क्या होगा कि it is just the change of origin, right? Constant force is simply the change. जैसे ग्रेविटी हो गया, फॉर एग्जांपल ग्रेविटी इज अ कांस्टेंट फोर्स. उसे भी अप्लाई कर सकते हैं. यू कैन अप्लाई virial also in that case. You can easily apply. For example, if in this u is there, you can directly apply virial and you will get the answer. Simple. You can. No doubt in that. ठीक है. चलो. The next concept of today, which is known as mixture of gases. So let's say you have a mixture of gas and there are two type of gases in it, gas A and gas B. There are n1 number of moles in gas 1, n2 number of moles of gas B. F1 is a degree of freedom of gas A, F2 is a degree of freedom of gas B. CV1 is a specific heat of gas A, CV2 is a specific heat of gas B. Both of them get mixed up. Both these gases are mixed. Then can I say number of moles is equals to N1 plus N2? Right? And now this is my final gas. In this, both kind of gases are there. Both A and both B are here. Now I am asking you the question, what is the degree of freedom of this gas? What is the specific heat of this gas? What is the Cp for this gas? So the simple relation is that Cv is given by N1 C11, N2 Cv2 divided by N1 plus N2. F is given by N1 F1, N2 F2 by N1 plus N2. And Cp is given by N1 Cp1, N2 Cp2 by N1 plus N2. Just these three things I want to keep in mind, because when we do the law of thermodynamics questions, this fact helps us. Okay? So this is known as mixture of gas. So these three formulas clear? No problem. This is just averaging, right? Perfect. So averaging thing. Teaser about tomorrow. So tomorrow I am going to cover laws of thermodynamics, especially first law and type of processes, especially isothermal adiabatic, and especially the numericals on it. So today class I could not do so many questions because today I wanted to give the brief theory introduction. Tomorrow I will give you some brief introduction of thermodynamics and many questions we will be solving. So next 1-2 days we will be more focused towards questions. I hope you enjoyed the lecture. That's all for this lecture. Any doubt you have, I am here for 5 more minutes. Yeah.